Hi students, welcome to my YouTube channel. Today we are going to discuss the problem number 3, that is based on to calculate the nodal displacement and stress in each element. So here we have the problem. Figure shows a bar subjected to a uniformly distributed load, that is P naught, taking Young's modulus E is equal to 70 GPa, area of cross section, that is area 10 raised to 4 mm square. We have to determine the nodal displacement and stress in the element. Here we have uniformly distributed load, that is P naught, and the Young's modulus is 70 GPa. So we have to convert this GPa to megapascal. Then area is mm square, no problem. And here the load is 100 Newton per meter. So we have to convert this Newton per meter to Newton per mm. Okay, so the direction is this side and this side is fixed and the length is 1200 mm. So first I will write the given data. Okay, given data, that is E is equal to, that is Young's modulus is given 70 GPa. After conversion we'll get 70 into 10 raised to 3 megapascal. Okay, now area 10 raised to 4 mm square, then length is 1200 mm. Next P naught 100 Newton per meter, so we have to convert this into mm, that is 100 into 10 raised to 3 Newton per mm. Okay, Newton per mm. So first we have to create the finite element model, that is FE model. Okay, the first step we have to create the FE model. FE model. As here we have the uniformly distributed load, I will consider it as single element. Okay, and this is the x direction, so I will take it as point number 1, that is node 1, and this is node 2. This is uniformly distributed load, that is element 1. Okay, so here we have the displacement q1 at node 1, and here the displacement is q2 at node 2. From here to here the length, that is 1200 mm, 1200 mm, and this is the direction x. Okay, then first we have to calculate the stiffness matrix. For that, elemental matrices, we know the formula, that is K E. Here E indicates the number of elements. Okay, so that is formula is A E by L E in matrix 1 minus 1 minus 1 1. Here in this problem we have only one element, so K is equal to K1 is nothing but K here, that is equal to area is 10 raised to 4 and Young's modulus is 70 into 10 raised to 3 whole divided by 1200, that is length 1 minus 1 minus 1 1. Okay, with the help of calculator you solve this, so we'll get 10 raised to 5 outside, in bracket we'll get 5.83 minus 5.83 minus 5.83 5.83. This is what K. Okay, then we have to calculate the global displacement vector. Next, global displacement vector. global displacement vector, we know vector q, that is defined as q1 q2. Okay, q1 q2. Similarly, the load vector, as here we have the uniformly distributed load. Okay, here we don't have any point load. Okay, so here we have uniformly distributed load. For that, load vector due to uniformly distributed load vector due to uniformly distributed load, that is f vector f is equal to p naught l divided by 2 1 1. This is the formula. So in this we have to substitute. We know the p naught 100 into 10 raised to 3 and length 1200 divided by 2 and into vector 1 1. So after solving we get 60 into 10 raised to 6, 60 into 10 raised to 6. Okay, now we got stiffness matrix K and displacement vector Q and load vector F. Then we have to substitute these three in equilibrium condition. We know the equilibrium condition. Equilibrium condition, that is K Q, that is equal to F. Here the K indicates the global stiffness matrix, global displacement vector, global load vector. Okay, as we have K value 10 raised to 5, 5.83 minus 5.83 minus 5.83 plus 5.83 and Q1 Q2, that is equal to 60 into 10 raised to 6, 60 into 10 raised to 6. Okay, as from the boundary condition we know that here this is fixed end, so displacement will be 0. So as per the elimination method, I will eliminate Q1 row and the column which is related to Q1. Okay, and I will write the remaining, that is 5.83, this one 5.83 into 10 raised to 5 into this Q2, that is equal to 60 into 10 raised to 6. After solving we'll get Q2 is equal to 102.915 m. Okay, now you can write nodal displacement vector, nodal displacement vector that is Q, as Q1 is 0 and Q2 is, just now we calculated 102.915, this is mm. Okay, this is the answer for first question. So the next sub question is stress in the element, stress in each element. So here we have only one element, so I will calculate only one. Stress in element, we know already the formula sigma is equal to E by L matrix minus 1 1 and here Qi plus 1. Okay, as we have only one element, so nodes we have 1 and 2, so I will substitute I is equal to 1, so obviously 1 plus 1 is 2, Q1 and Q2. So sigma 1 is equal to, that is sigma, as we have only one element, sigma is equal to E Young's modulus 70 into 10 raised to 3 divided by length is 1200 minus 1 1 and displacement at node 1, that is 0 because of fixed point, and displacement at second point just now we calculated 102.915. Okay, so first we have to solve this, and we have to multiply with -1 and into 0, that will be 0 because as it is 0. Then we have to solve this, and we have to multiply with 1, and then we have to multiply with this. So we'll get sigma is equal to 6003.375 megapascal. Okay, as they asked in the question, nodal displacement and stress in the element, so they calculated this is the displacement q1 and q2, and this is sigma.